All right, welcome everybody. So here is homework 13, and I've just given you the cover page for homework 14. If you're following along in the course schedule, you may notice that homework 14 I'd actually listed in our original plan for the semester as being due on Monday, November 28th, which is the day immediately after the Thanksgiving break. But just because I'm such a big-hearted, nice guy, I decided to push that back 2 days so that you're able to procrastinate that to Tuesday night instead of to like interfering with your holiday. So anyways, you can enjoy your Thanksgiving double well knowing that your project is finished and you can worry about the homework later, right? All right. Oh, well, I didn't expect applause, but yeah. Wow. I could get used to that. How about let's push back more deadlines. No, I'm not that nice, as you already know. All right, so today we're going to be talking about cost estimation and a new chapter in the book, chapter 15. So the only other announcement I wanted to remind you of is that next week on Monday we're going to have a quiz. And as has been asked previously, you don't need to bring in the computers for the quiz. I mean, you're certainly welcome to bring your computer that day, but you're not going to need it for the quiz itself. That'll be a pencil, paper, and calculator quiz. Any questions before we get into it? All right. A few years ago, I did a research project for the West Virginia Department of Transportation related to the scour of foundations at bridge piers and abutments. And what this is showing, it's maybe a bit hard to see because it's so bright in here, but this bridge is founded on rock, but when the water is moving really fast because of a flash flood event, then there's enough energy in the water to actually carry away broken bits of rock that are underneath this concrete foundation. So that over many years, the structural integrity of the bridge is threatened by the fact that the foundation is undermined. And so it's a real problem. It's something that the folks at the Department of Highways worry about. And so they devoted about $300,000 to a research project to figure out what causes the problem, how widespread is it, and what can be done to calculate how long a bridge has until the foundation is undermined. So the majority of that money, well, maybe not the majority, but a really big part of that money was spent drilling samples of rock near the bridge sites. There were 15 sites across West Virginia. There are 10 districts within the Division of Highways, and we had at least one project site in each of the 10 divisions in the Department of Highways. So it was really distributed, and so at each one of these sites we had a drill rig come in and take core samples where they're drilling down through the pavement to get at the rock that's there, and so it was really costly. We had a drilling crew of about 5 or 6 people. They had to put up, maintain traffic by putting safety signs, and anytime there's a construction project or interfering with the free flow of traffic, they have to have people to wave them through and so on. These core samples that were obtained had to be transported back to Marshall, and then over in the engineering lab building they were sectioned, cut up into little pieces, and then they did a geological test called the Modified Slate Durability Test, where basically they put it in a rock tumbler and see how long it takes for these rock samples to break. And it's indication of the overall strength of the sample. So a big part of the budget was spent on this real activity of the project, going out into the field, getting a sample, testing it. But a lot of the project money was spent on other things that you wouldn't necessarily think is related to research. Some of the project money had to be used to support the facilities that the samples were stored in, or the facilities that the testing was conducted at. So here's a picture of the lab building. And so it would be really confusing for the Division of Highways when they received a bill if it was itemized for every single thing that was used to support the project. Think of how confusing it would be if I had to keep track of how many pens I had used during that project, and I had to keep track of the amount of electricity that my computer had expended as I was doing calculations on the stream flow energy. You know, the lights have to be left on for the research to be conducted. There needs to be an accountant to manage the grant, and there needs to be a computer available to do the project. But of course, at the end of the project, it's not like we throw the computers away and get new computers for the new project. There had to be meeting facilities available because we had annual progress meetings with the Division of Highways and occasional conference calls to bring them up to speed on what we'd been doing. So if you think about the way that money is spent on a research project or in business or just about anything else, there are costs that could be, broadly speaking, divided into two categories. Like the kinds of costs that are directly related to what you're doing, the main task, and then the kind of costs that are kind of support costs, and a little bit more difficult to say how many pens and pieces of paper it takes to do a research project. So we can divide those costs into the direct costs, which are specifically related to the work activity or the output that's being generated. So we could say, for instance, how much sugar is required to make 1,000 Twinkies. Or we could say how much packaging is required to make those Twinkies. Or even how much labor it goes into producing that output of the work activity. Speaking categorically, those can include the materials, labor salaries, production expenses. But the thing that's a little bit more tricky is finding ways to account for what we call indirect costs. Indirect costs can't be specifically allocated to a task, and so instead of trying to keep a really lengthy and detailed log of every little thing that's used, you just basically develop a percentage and say that the indirect costs are a certain percentage of your direct costs. And there's something called an indirect cost recovery factor that you'll apply. So if you think about computer systems, accounting, the salaries of supervisors, we don't say that it requires a certain number of accountants to do our research project. I mean, you probably could, with enough effort and study, figure out exactly how many person hours were needed over the course of any particular project, but there's just a simpler way to handle it, and it's these percentages. So at MIT, they actually, being MIT, they studied the idea of indirect costs really carefully so that they could figure out the money that they're taking to cover the overhead, as it's sometimes called, where did they end up spending it, and what was it allocated on. And at MIT, they found that, broadly speaking, the majority of it was supporting the facilities, so that's the equipment and the buildings, and a smaller fraction of it went to administration, which is the supervisory and accounting kind of roles that are played during a project. Now here at Marshall, whenever we do research, 45% is the cut that goes to cover the indirect costs. So what that means is if I bring in a $100,000 project from the outside, then $45,000 is taxed, is how you can basically think of it. Marshall takes $45,000 and they keep it to cover the building, the electricity, the computers that they provide, the telephone, the internet access, the conference rooms, and all those other things that we've already talked about. And so then my budget to pay for things like sending a drill crew across the state or buying new equipment or paying for like a student helper to do the testing, the leftover amount would be $65,000 out of that $100,000. And so that's the interpretation of those percentages, is the indirect costs go to cover all those things, and it's just on a percentage basis of the direct costs, which we can allocate a little bit more easily, since those are the things that we're actually buying. So any questions so far about what is a direct cost and an indirect cost? You feel like that's something you could do a short answer on? All right. Well, we're going to look at several different ways of estimating costs today. You know, because when you conduct a project, you have to know before the project begins about how much it's going to cost. You have to develop an idea of what the budget is going to be, and sometimes you have to, even before you make a new product, figure out sort of what target price you want to have for it. So think about in the smartphone market, which is very competitive. There are some smartphones that are very inexpensive, like the smartphone that I use is a Moto E. It only costs about $80. It's a great phone, but it's cheap compared to like a brand new iPhone, which may be $600 or $700. There are different markets. The phones do different things, and so the manufacturers, as they're building a phone, they have a final target price in mind. It's not like they are just blindly slapping components together and then are kind of surprised at the end of the project of what they need to sell it for. It's very deliberate. The bottom-up approach to cost estimation is a way of adding up your actual expenses, and here this illustration is showing that the direct costs include the equipment that's needed to do the manufacturing, so that would be whatever robot is making circuit boards and preparing the screen and so on, the direct materials, the things that it's actually made out of, the direct labor, which are the people in the factory that's assembling the phone. Maintenance and operations would be related to transporting the product to market. And then the indirect costs could be advertising, it could be accounting, the salaries for the administrators, the rent on the building for the factory, and so on. Electricity might be included into the direct costs. And so they have an idea of their total costs when you add up all of the pieces that go into a phone, and then you figure out what you want your profit to be, and then finally the output of this whole process is knowing what price you're going to have to set for the item in order to cover the costs and give yourself the profit that you like. Now this bottom-up approach is something that Apple is able to do because most of the products that they put into the market are unique. They're not commodities in the same way that a lot of other electronics manufacturers are kind of interchangeable and not that innovative. And so the other approach that a lot of more commodity type manufacturers use is the top-down approach. Now you can think of this as if you're in a very competitive market, you use the top-down approach because you already know about how much you can sell your item for. So when Motorola was developing this phone, they said, our competitors are selling cheap phones with LTE for around $80. So $80 is the maximum we're going to be able to get out of such a phone. Let's keep 10% for ourselves. So if we have $8 profit, now $72 is how much we can put into the indirect and the direct. And so with that budget in mind, they start to figure out how much they can afford to put onto the screen, how much they're going to put into the RAM and the CPU, and so they're kind of assembling the components at the very back of their mind, always remembering what price would be competitive in the market. And so bottoms up means that you're not necessarily worried about the price as your first thought. You're focusing more on the actual costs of the items. And so in markets that are not yet well developed, the bottom-up approach is what's taken. So at the beginning of an industry where you're having to build something new for the first time, or where you have a monopoly, you can apply the bottom-up approach. But in a more competitive market with lots of interchangeable substitutes, the competitive price approach, where you know you can sell it for, and then you kind of have to allocate all of these costs so that if you can have efficiencies, like if you find ways to save money in maintenance and operations, then you can either keep that as more profit or you can lower your price. And so That's one aspect of cost estimation, is trying to think about the project that your company is entering, whether it fits one of these two models. And when you estimate the price at the beginning that you hope to sell it for, is that a result of knowing the cost of the components, or just knowing that if you're too high, nobody's going to buy the item? Here's a completely different aspect of cost estimation. And this is kind of related to what I was saying earlier, that if you really wanted to, you could find out how many pens is required for a project and how many sheets of paper you're going to use during the project. Like at the beginning, even before I started that research project for the Division of Highways, I could have done an analysis of how many sheets of paper I'm going to use for the project. And I could talk to a lot of other researchers and ask them how many sheets of paper they had used. I could go to the accounting office in Old Main and ask to see purchasing records and do some calculation, make a spreadsheet. But in the end, it obviously would be kind of a waste of time, because the amount of savings from having a really good estimate for how much paper is going to be used versus the cost of preparing that estimate, it would be uncalled for. So that's what this figure is illustrating. It's that if you spend only 10 minutes developing an estimate, it's not going to be very accurate. So the vertical axis here, the accuracy of the estimate, in 10 minutes maybe I can only be accurate to within maybe about 30% of the actual cost. And so what you have to ask yourself in such a situation is, what is the risk of getting it wrong? Like, what if I underestimated how much money I'm going to spend on paper? That's okay, because paper is so cheap, it doesn't matter if I'm 30% off. I can just pay the extra 30% and it's no big deal. And so a 10-minute estimate maybe would be perfectly fine in such a trivial situation. But then there are other cases, like this building that we're in. They did calculations before they started actually constructing it. They knew how much steel was going to be required. They went to the plans and they added up how much steel, probably on the basis of different sizes and the weight of that steel. And so probably that cost estimate for something as important and expensive as the main construction components for a building, they may spend 3 weeks on that, because an engineer's time for 3 weeks is worth having the best accuracy possible, 5% accuracy, because if you end up allocating too little to that, the consequences could be that you prepare a bid for the project, and the contractor who said that they'd build this building for $55 million, maybe they should have said that they'd build it for 57, but they didn't spend enough time on their cost estimates, and so they accidentally underbid, and then they're really in financial trouble. And so this figure is just kind of conceptual. Like, this doesn't mean that in every case it takes 1 week to have 10% accuracy. That's not what this figure is saying. But what this figure is saying is there's a trend, and on the far right side of the horizontal axis, there's a point of diminishing returns. It begins to flatten out, because if you spend 3 weeks or 3 months, you may not have much better estimate of how much something is going to cost. And so you have to balance the estimate accuracy with the risk of getting something wrong, like how expensive the item is and what effect it will have if your estimate has error in it. So here it says one should balance the need for accuracy with the cost of obtaining accuracy. And the cost of obtaining accuracy is time, and the value of whoever is being paid to do the research. So you feel like you could explain this figure? Because remember, one of the things I like to do on quizzes and exams is get people to explain figures. Because it's one thing to just plug numbers into formulas or to set up a spreadsheet the way you've been shown a spreadsheet. But if you can explain a concept, then it shows you really understood something. Here's another figure, and it tells an important story. Life cycle costs are all about when you're going to spend money, and even before you've spent money, when you've made a commitment or a decision that takes you down a certain path. So I want to point out what a couple of these different blue lines mean. The blue line that's at the bottom, let me show you this one, the one that says cumulative life cycle cost. This is the money that you've actually spent. And there are different phases of a project. The acquisition phase is before the thing is built and the construction is completed. So again, using this building as an example, at the beginning there was a definition of requirements that the architects conducted. They had meetings with the people who'd be using the building to find out what rooms do you need, how big should the classroom be, how tall should the ceilings be, how much space do you need to have in the fluids lab versus the transportation lab, how large should the ceilings be in the structures lab. They asked a lot of questions about how the space would be used. And so that was the needs assessment. The next phase was they did a conceptual design. Now that wasn't to the level of knowing exactly how thick each beam needed to be and exactly what carpet we'd have in the building, but the conceptual design was more of just a general layout where they could show some pictures to check and see, does this look okay, and are the room the room layouts going to be consistent with what people need. That conceptual design led to the detailed design, and then that's where they really made decisions like the color of the paint on the wall, exactly what kind of outlets there were going to be in the room, which tables should be purchased, and during that detailed design, a lot of decisions were made that would affect the project later on, like you're making a firm commitment that things are going to go in a certain direction. So those are the three components of the acquisition phase. The operation phase is when the item is actually being built. Once the groundbreaking is started, that's the beginning of the construction phase, and then when they have the ribbon cutting, like when the building is finished and they have the big ceremony to inaugurate its use, that is the operation phase of the building. And then at the end, the building will be torn down and they'll take all of the construction debris someplace and landfill it. So those are, broadly speaking, from the life cycle, from cradle to grave, they sometimes say. When you're thinking about the material components, and even before that, just the idea of something, all the way to when you're done using it and you have to find some place to put the leftover remains of it. Okay, so this bottom blue line is showing where you've actually spent the money. Since a needs assessment, just a couple of meetings with the architects, you're not spending very much money for those meetings. And so you'll notice that that line is pretty flat because you're not spending much money during that needs assessment, but the line is getting more steep during the conceptual design because that takes more time. It's more rigorous. They're getting out their computers and putting some sketches together. Where do you spend a lot of money is production and construction. So this line starts being very steep when you're actually buying the materials, paying the contractors, putting down carpet, purchasing lab equipment. And so this gets really high during the construction phase. But then it starts to flatten out again during the operation, maintenance, and support phase because although it still costs you money for utilities and upkeep of the building, it's not nearly as costly as when you first built it. And then finally, retirement and disposal, it's flattened off a lot because you still have to pay for someone to haul away the item when you don't want it anymore, but not nearly as much as when you were operating it. So that's what this bottom blue line means. It's the actual money that you've spent. The line above it, this curve, is related to when you've made a decision to spend a certain amount of money. So it's not that you've spent it, but you're kind of at the point of no return because of the decisions that you've made. And so you'll notice that it's always above the cumulative life cycle cost curve. And so you think about when does it get steep. During the design phase, you're deciding how big the rooms are going to be, what equipment is going to be purchased, and so you haven't actually spent the money yet, but you've made decisions about how the money is going to be spent. And so if you have made a commitment, you've lost the opportunity to save money. For example, what if they decided that there's a lot of extra seats in this room? We don't actually need to have 60 seats in this room. We could have done with maybe 45, or on a Friday, maybe 35, right? So the room is too big, but we've already made the commitment about how large it's going to be, so we can't save any money after the design has been fixed. And so that's why this line is to the left of the cumulative life cycle cost line, is because it's not that we've spent that amount of money, but the opportunity for any savings is gone. And then that's what this final curve is its potential for cost savings. And it shows that you've got a lot of potential for savings in the needs assessment. Like if they decide, well, actually we don't need that thing after all, and they decide to eliminate some expensive lab that someone had proposed, if you eliminate it, then you save loads of money. But if you realize once the thing has already been built that you didn't need it in the first place, there's no way to save that money. The opportunity for savings is gone. And so this curve gets lower and lower, and by the end, there's not much you can do during the operation and use phase to save money. I mean, they can raise and lower the thermostat a few degrees and save a few pennies on heating and cooling costs, but that's a small fraction of the millions and millions they spent to build the facility in the first place. So any questions about this life cycle cost figure? It's taken from your text, and I'd encourage you to read through the book and sort of reinforce the concepts that are behind this. One of the main points that I hope you'll take away from the discussion we've had is that it's easiest to save money at the beginning of a project. The longer you get into the project and the more decisions that have already been made, the more challenging it is to change course and find meaningful savings. All right, so those are just sort of concepts that support cost estimation in general. The main problem-solving approach that we're going to be looking at today is called the unit method. And what the unit method does is it gives us a way of finding total costs by knowing how much the cost of one unit is. So if you look at the carpeting in this room that we're in, it looks like these carpet squares are about 2 feet by 2 feet. And so what would you guess one of these carpet squares costs? Just a single 2 foot by 2 foot panel. Any ideas? How much? 20 cents? Boy, I don't know. I think it might be a little higher than that. $2. Let's say $2, for example. Okay, so if it's $2 for this carpet panel, what the unit method says is, well, you know the cost per unit, which is U, $2 per unit. We could find out how much carpet budget we need to have for this room by just counting up the number of squares. Or it could be operating a car. The unit method is used for that. If I drive my car to the South Charleston campus for a meeting, for example, the university will reimburse me on the basis of how many miles I've driven. If you build a highway, one kind of, I don't know, round estimate for the cost of constructing a highway when you don't have a bridge, just the paving and the earthwork and so on, about $6 million a mile to put in a highway. Constructing a house, around $200 a square foot. So you get an idea that you can figure out your total cost by knowing how big the project is going to be, how many miles you're building, how many yards of concrete you'll be pouring, and so on, and then multiplying the number of units required by the cost per unit. It's the simplest way to estimate costs. And that's what you're going to do with today's in-class exercises. You're going to use the unit method to estimate the cost of building a pipeline for part 1, and I give you the cost of steel, machinery, labor, and indirect costs so that you can find the overall expense of 150 sections of a natural gas pipeline. And then on the back side of the paper, once you've finished part 1, here on the back side we're going to be doing a decision-making analysis. where you have to choose between two different methods of making iPhone cases. One of the methods uses a cheap, low-grade plastic that's pretty inexpensive but has more rejects. And then the alternative method uses a more costly plastic, but it's more efficient in several ways. So you're going to be using the cost estimation method of the unit approach to decide which way is better. For part one, you should expect your company to budget $566,700 to build that pipeline. The components of the costs are shown on the screen. I want to show you one of the key ideas for part two, and that is that if you know how many units per month you're making 8,333, and that with the cheap plastic you can only do 57.1 parts per hour, then you can find out how many hours it's going to take by dividing 8,333 by this 57.1 units per hour. So if you do that division, it'll tell you the number of hours of labor required, and our cost for labor is $15 per hour. So that's how you'll find out the overall labor costs for the cheap plastic. The labor costs for the more expensive plastic are going to be lower because you won't have to work as many hours. You're able to do more parts per hour. You're able to do 102.9 parts per hour, and so for the same number of units that you're making in a month, it'll be fewer labor hours. Even though the high-grade plastic is more expensive, it's still worth going the high-grade route because the overall costs are going to be lower. You're spending just a little bit more on plastic. You know, instead of spending $88 a month on the plastic, you'd have to spend about $450 per month on the plastic. But then it leads to a lot of savings in your labor and your other costs because you're not having to operate the factory for as many hours during the month. So you can send everybody home early and keep the savings. And the savings on an annual basis, if everything so far is on a monthly basis, and so if we translate that into an annual basis, it works out to about $15,000 per year that you'd be saving by switching to the higher cost plastic that allows you to operate more quickly. Before you go, let's take one last look at these announcements just to make sure we're on the same page. You've got a quiz on Monday. The project is due 7 days from today. At the beginning of class, you should submit your project report. And then you'll have a big sigh of relief over Thanksgiving break and coming back on Wednesday the 30th with homework number 14. So I'll see you on Monday.